Okay, Assalamualaikum dan selamat malam. Saya saja mula lambat sebab saya tunggulah semua masuk dulu baru saya start. So, okay, we're going to start our lecture tonight and continue from previous case study happened in Shanghai for high-rise building collapse, building number 7. So before we start, just to ask you, have you had any experience doing simulations in numerical software, either in structural or the technical or any kind of the software? Have you had any kind of experience? How do you deal with the problems and how do you solve the problems before you start having the final results? Can you share based on your experience? What was the first thing or what is the first thing you do before you carry out details analysis?
Tak pernah guna doktor.
What is it?
Tak pernah guna software.
Never encounter any kind of the geotechnical software or any kind of software in your area, structural or pavement or whatever it is?
For structure design, basically we use Esteem and Portal lah.
But
So for
Esteem is
geotechnical, I tak pernah design for foundation for geotechnical part lah.
how do you solve your assignment one? If I'm not mistaken, because Dr. Conscience has shared one link from web-based. There are many free software available for you to have a try and doing the analysis by using the free software. So how do you solve your assignment one? Is it you doing the analytical solutions or you are doing by numerical simulation?
For me, I use manual calculation lah. Use the formula.
The analytical solutions. So that's okay,
Yeah.
never mind. You can have your own I mean that if you are comfortable using the analytical solutions, the theoretical assumptions or whatsoever, you can proceed with the theoretical or analytical solutions. If you are capable in doing the simulations by using any kind geotechnical software or any kind structural software, it also welcome for me is that if you are encountered with too many software, is it good because you can see what are differences between one software to another software, and if you can try, for example, in geotechnical area, we are commonly use Platsys as our main software tool, and okay, for geotechnical area, basically we can use Platsys. There are 2-dimensional or 3-dimensional geometry model using the Platsys. If you're not capable or familiar with the Platsys, you can also use Slope W. This is only for solving slope stability analysis, and there are differences between Slope W and also Platsys because Slope W adopting limit equilibrium method, meanwhile Platsys adopted finite element method. Of course, when there are two different solutions in part of the LEM and also FEM, there are some different assumptions you can start off to solve your problem. Same goes here because tonight our problem will be solved using the numerical solutions. So before you can doing the numerical analysis, you need to understand what exactly the problems are and then what are causes to the problems and how are you going to start off doing the simulation by basic assumptions. For example, looking back to the problems and what are the things you can encounter from the site investigations or forensic investigations. Not to forget as well, if you are not familiar with the slope W or Plaxis, you also can have some sort of abacus. Another one is a console or any kind of the software you are preferable. So let me share to you my screen tonight. This will be on continuations from previous lecture. So we're going to start off with investigation, numerical analysis, 3D finite element, and the method to simulate the process of excavation and dumping. So just remember, the case study had already occurred. So this kind of the researchers did on back analysis, or what we call it, they tried to find out what were the main reasons or causes to the problems that bring to the buildings collapse. So in this part, to details or to understand this kind of the problem, the best thing is using the numerical analysis or simulations. So if you look at back to the problem, so there are something we can take into our considerations where there are two different directions that causing to the failure. For example, at the north side and also at the south side. So concurrently, there are few constructions activity occur at the same time. So we start off with the north side. So remember again, before this, you can see on the left side of this slide, on top and as well at the bottom is the diagram showing to you the problems. We have the building number 7 and having some sort of the pile below the structure. And at the north side is the dump site area. Meanwhile, at the south side is the excavations or excavated for underground car park. So looking back at the south sides, they were provided soil nailing to retain soil from movement, but never realizing that the problem starting at the south side where they were few what we call it a dump site occurred where the first stage with the height of embankment around 4 meter, and then at the second stage the total embankment height is 6 meter. So the increasing of the embankment during the time has causing to the lateral movement resulted to the building's collapse. And at the bottom of this figure showing to you the average undrained shear strength of the soil. So the importance of the undrained shear strength of the soil is to be an input for numerical analysis or whatever we call it as analytical solutions. The simple thing is that if you are preferable to use analytical solutions, we try to adopt the simple equation. We call it here as the Zerge equations for bearing capacity, saying that the bearing capacity factor is a 5.14, and then the undrained shear strength is around 25 kPa. When you multiply with a 5.14, resulted to 129 kPa. So how do you get that the undrained bearing capacity 25 kPa? You can see at the bottom of this slide, there were many field informations regarding to the site area, soil profile, the unit weight, the water content, the void ratio, the vein shear strength. So the average vein shear at the 10 meter depth is 25 kPa. So the value is being inserted to the formula and bring to you the answer around 129 kPa. And also, assuming that the field of the embankment has given the overburden stress around 63 kPa. So when they did on the calculations for the soft clay, it is given that the strength of the soil is 157 kPa, and the ultimate bearing capacity of the soil at the end bearing is equal to the CNC, which is around 129 kPa. So what I said just now, 129 kPa is referring to the bearing capacity of the soil, which being calculated at the base of the pile footing. So when you see here, the soil strength is around 157 kPa. Meanwhile, the end bearing capacity of the pile is 129 kPa. So therefore, the stress coming from the soil is bigger than the capability of the pile to carry the load. Therefore, that's resulted to the failure. So this is what we have occurred in the north side of the collapsed building. and never know that the calculation doesn't enough to indicate what's the real problems or what's the real things happen at the site. Therefore, that's coming to the numerical simulation to try or to understand what are the construction activities gave to the problems. And here, when you go in details, before that, if you have something that we can refer on the south side is the informations about the excavations, and at the north side there are similar informations from the soil profile. And here again we can see these are the things on the locations of the pile, and then the embankment or the total length of the pile provided from the site area by these researchers. And again, to estimate or to understand what will occur during the time, so they do the cross sections of the building and also the cross area. So you can see these were the 13-story building, and also the excavation site at the north side, and also the dump site, sorry, the excavation at the south side and the dump soil at the north side. So the simulations in 3-dimensional with the geometry length and also the height of the soil profile around 160 by 170 by 50 meter. So you can see here, actually these colors indicates the soil profile at the particular depth, meaning that the soil having multi-layers brings to different soil properties, and these structures, this high-rise structure will build on the soft soil, which means that you can see the variance of the undrained shear strength of the soil. So the layout of the problems is given at the figure 10b. What's important about here, when you see on the finite element method, is the meshing size of the element itself. So every single nodes of the elements are given you the stress and strain nodes. So every point of this finite element nodes will tell you the difference value of stress point and also strain at this particular point resulted to the strain and also resulted to the deformations. If you are looking the deformation at that particular nodes, you just click at the point, so you can see the deformations occur below soil or the deformations occur below the structure. So this is among advantages using the numerical simulation instead of using the analytical solutions, because the analytical solution cannot give you detailed visualizations what are happening on top of the soil or below of the soil. So the schematic diagram of the problem being drawn again at the B sections. So here you can see the dump soil and also the excavation size. Okay, the first thing when you want to do the analysis by numerical simulations, you have to set up the assumptions. What are the dimensions of the problems, and then the geometry of the problems, and also what are the coordinate for each of the point, and also the structure and so you're going to build on the surface of the element model. So when you have decided all these things and few assumptions, for example, water table effect, and then the surcharge effect, and the boundary conditions and meshing, etc., you can start doing the numerical simulations. Basically, for numerical analysis, there are three important stages. The first thing is the input stage, and from the input stage, all this data bring to the second stage. We call it as a process. In this process stage is a stage where calculations are being carried out. For example, what you want to calculate the effect of the water table, or you want to calculate the effect of the loads on the structure or loads on the soil. It can be at this stage number 2. After stage number 2 is completed, so the result will bring or will be displayed in the output. So in this numerical simulations, the best thing is that the visualization is not on the static image. It can be three-dimensional images, and then you can look at the result at certain point you are looking for, and the result also can be displayed in table or can be displayed in the graph. It also can be displayed on the contour images. So it's very interesting if you have some experience solving your problem using the numerical simulations. And these are the very common thing. At the first stage of inputs, you need to have some sort of the geometry model, and then the dimension itself, you need to know what are the input for soil, inputs for structure, and then what are the stiffness, what are the Poisson ratio, and what are the unique weight of the soil or unique weight of the structure, for example. What are the model that you're going to use, for example, elastic model for structure, and then more column model for soil. So these are the things that you need to define or set in the early stage of the numerical modeling and simulations. Same goes to the loading, boundary condition, meshing, and etc. Once this is done, so all these things bring to the second stage process. At this process, you can select you want to calculate as part of deformations, or you want to calculate as a plastic strain, or you want to calculate as a safety factor, or whatever. After completed the calculation stage, and the result can be displayed in the last stage, which is output. Okay, numerical simulation, kalau ikutkan me myself teaching numerical or advanced geotechnical engineering to undergraduate students, some of them very afraid when heard about the modeling and simulations. Actually, kalau ikutkan sebenarnya kita tak boleh nak avoid ourselves from facing or having this kind of the solution using the numerical tool. Because now, kalau the students can play a game by handphone or technology, some sort of this one, meaning that they also capable to solve the problem using the numerical simulation. That's my assumptions. Kalau kata students afraid using the numerical tool, so we need to give them some encourage, advice, the advantages knowing about this tool. Because for me, it's become an advantages kalau you tahu guna software lah. Kalau you tak tahu guna software, dia jadi macam ke belakang sikit lah. Sebab kalau kita tengok kebanyakan complex problem, dia tak boleh selesai dengan simple analytical or mathematical solutions. Sometimes the numerical software is needed due to the complexity of the mathematical equations. So the mathematical equations cannot be done easily as one linear equation. Sometimes it can be solved using the quadratic integration or differentials. So when you are having a problems that very complex in the one's element or in the very large of the structure, so the best thing to solve the problem using the numerical simulations. It is true, it takes time to understand, but the self-learning is the best teacher for person to have this capable doing simulation using software. Something that, for example, geotechnical engineering, the problem cannot be seen on the surface. Therefore, in order to understand what's the soil behavior below the surface, we need this tool. This tool will tell you what's exactly happened to the problem or to the real site conditions. For example, this problem for case study in Shanghai, actually they want to know what are the causes of the problem. Is it the process of construction activity claimed by the other said that the authority not following to the standard? Therefore, by using the numerical simulation, they can investigate, is it the claim true or untrue? So you can see after this, how they set up the stages of construction to tell is it through the claim about the unfollowing to the standards or guidelines given by the local authority. So for this year, you can see that the simulations, the process of excavation on one side of the building and dumping on the opposite sides. So this is the schematic diagram and our problem. The special attention was paid to stress created in the pipe piles by excavations and dumping. So the length of the mesh in the lateral direction was 170 meter. The width X and depth Z were 160 and 50 meter. In the analysis, the subsoil was modeled by 15 knot wedge soil elements. So returning walls was simulated using 8 knot quadrilateral shell elements, whereas the soils were modeled by ground anchors. For both foundations beam and structure beams, 3 knot beam elements were used. So the 118 pipe piles were simulated using the embedded pile models, which consist of beam elements connected to the surrounding soil. And the 3D model consisted of 65,439 elements and a total of 181 nodes. So you can see kalau kita buat one linear equations, kita tak nampak lah elemen-elemen ni, kita tak nampak berapa banyak nodes yang terlibat untuk menyelesaikan finite element. The finite element method sebenarnya dia coming from the one linear equation stress and strain relationship solving by matrix form. However, kalau kata kita nak tengok one element dalam 3 dimensions, so ataupun complexity problem in 3 dimensions, one linear equation, it is not able to analyze the case. So therefore, this kind of the stresses and strain acting to the plane, for example, 6 faces of the plane elements. So coming to the matrix forms, let's say we have 6 by 6 matrix form. So you can see dia punya matrix equation and the solutions problem tu dia akan jadi panjang. So kalau kita nak selesaikan by hand calculation, it takes time. Dan bila salah, we have to recheck and redo again the process. So it takes time and very tedious. Sometimes cannot be done in 1 hour. So bila kita selesaikan this problem menggunakan not simple tapi lebih kepada advanced software ni, dia lebih cepat lah. Kalau kata kena gayanya, dapatlah jawapan cepat bergantung kepada laptop juga. Kalau kata laptop tu agak storage dia tak besar, kemudian dia punya processor dia pun slow, so simulation pun akan ambil masa yang lama. Lagi besar problem you, image you lagi lambat lah, ataupun lagi fineness mesh yang you assign kepada simulation model tu lagi lama lah dia nak run the calculations. So in here, kalau you nampak the details of everything, because these are very important and this problem is a soil structure interactions. So bila soil structure interactions, dia kena look at from the soil itself, and then dia kena tengok pada structure itself, the properties of the soil and also the properties for the structure. So this structure pula is not only about a single ataupun simple foundations like as shallow. So it is about deep foundations, dan juga kalau kita look at back from the previous slide, dia adalah lebih kepada hollow span pipe. So bila hollow span pipe, itu pun memerlukan kemahiran dalam modeling dan juga good knowledge about geotechnical problem untuk you assign the material, the model dalam software tersebut. So in part of that ones, selain daripada identify structure soil properties, we need to know as well the boundaries of the problems. So remember, kalau kita buat simple calculations for the structure, commonly kita akan ada 3 types of the boundaries, for example roller, kemudian kita ada pin, kita ada fixed ends. So same thing here, dia punya implementation dekat software pun sama, you kena identify lah, you nak allow for deformation, movement at what directions, kemudian you nak kenakan boundary apa, is it roller or is it pin or is it fixed end. So kalau fixed end maknanya takkan ada deformations lah, laterally ke vertically ke apa kan. So kalau you assign for roller, so apa yang kita akan dapat lah. So all this based on the assumptions and based on problem yang kita adalah. So untuk case yang soil parameters ni, so dia dah list out few parameters involved. So from the beginning, from the top sehinggalah ke beberapa kedalaman iaitu 50 meter ni. So you can see that tanah ni is very soft soil. In part of the strength is a very low shear strength. So bila dia low shear strength, maknanya we need to do something lah, sama ada soil improvement ke ataupun soil reinforcement. So at the south side ni, kalau you nampak sebelum dia nak buat underground excavation, so dia dah letak retaining wall as a soil reinforcement menggunakan soil nailing. So dalam this case, after identifying the depth for every particular soil types, and then they also need to know the unique weight of the soil. So you can see the unique weight of the soil not constant from the first meter at the ground surface to the end, around 50 meter. Same to the undrained shear strength, the effective cohesions, the latency angle. This is the what we EU is the undrained elastic modulus, E effective elastic modulus, Fs is the ultimate skin frictions, Fp is the ultimate end bearing. So these are the parameters for soil. Maknanya kalau talking about shear strength parameters, selalunya kita nak tahu what is the effective C, what is the undrained shear strength, and also what is the effective internal frictions angle. And then the EU E prime ni dia lebih kepada elastic modulus, because as I said earlier, bila you kenakan loads pada structure, dia akan hasilkan stress. So bila ada stress, dia menghasilkan strain. So the deformations rely to the two behavior, elastic dan juga plastic behavior. So the elastic behavior controlled by these two parameters, yang modular dan juga Poisson ratio. Meanwhile, for the plastic behavior is controlled by three parameters, iaitu dilatancy angle, effective cohesion dan juga effective dilatancy angle. Assuming that the soil is fulfilled to the more column failure criterion. And FSFP adalah kalau kita tengok balik theoretical from the pile bearing capacity, Q ultimate sama dengan QB plus dengan QS. So QB is the end bearing capacity, QS is the skin friction capacity. So FSFP tu dia punya coefficients to calculate the ultimate skin friction dan juga ultimate end bearing capacity. Okay, apa pentingnya parameters ni untuk kita masukkan dalam modeling kita lah. So dalam part of the construction sequence, so these are the assumptions assuming by these researchers, yang mana firstly they're going to assume that the initial stress conditions were generated firstly, and then the construction starting by having foundations, piles installations, and the building. Kemudian the next construction sequence is a dumping of soil to a height of 4 meter on the northern side of the building. And lastly is the constructions of the retaining wall, excavations and dumping of soil to the final height of 10 meter. So ini adalah second stage. So dia ada difference, there is a difference results kalau the constructions activity ni wrongly set. For example, kalau you tengok at the north side of the building ni, dia punya dump site ni ataupun dump soil ni dia ada dua. Satu yang 4 meter, kemudian satu lagi yang kali kedua dia dump around total height total height is 10 meter. Let's say lah kalau kata kita buang nombor 3, kita assume construction sequence ni dia terus buat dia terus letak sebagai 10 meter ataupun dia can split 10 meter by assigning 5 meter, 5 meter. Itu pun dia boleh bagi difference result to the total deformations and of the analysis. So this one macam mana dia boleh dah identify dia ada first stage ataupun the second stage is due to the forensic activity carried out ataupun kita panggil sebagai post failures. So bila dia went to the site, they found that two failure modes accounted at the site, and the first coming from the first stage of dump, and then the second stage from the dump created to the deformations of the soil. So these are the assumptions made to look at the constructions activity simulations. And on part of the building or the results coming from here, look at the bottom left side. This is what they had from the analysis, where something moment created at the right side and also negative moment at the left side. So the negative moment and also the positive moment indicates to the bending moment for the pile or the the pure bending capacity. So it shows that for the first stage dumping and then the excavation and second stage dumping, given you the moments at the pile itself. So a positive bending moment means that the pile bends toward the surcharge loading sites, whereas a negative one means that the pile bends toward the excavations. So it's explained here why they has M positive and also M negative. So it shows as well, after soil had been dumped to a height of 4 meters on the northern side of the building, the maximum bending moment of the pile reached approximately 58 kilonewton meter. So this is the positive moment. And the value is within the pure bending capacity of the pile, suggesting that the pile had likely remained intact at the point in time. So this is consistent with the fact that the building was not damaged in the first 6 months after the soil damping. So this is true. The maximum positive bending moment in the pile developed approximately 10 meter below the ground surface. So this is what it said then. Di bawah 10 meter kedalaman, didapati ada negative moment which head to the excavations. So what does it mean? So the maximum negative bending moment in the pile occurred around 14.5 meter below the ground surface and corresponding to the interface between the soft and firm strip clays. So in addition, the absolute value of the negative bending moment exceeded the maximum positive bending moment. So this implies that the foundation pile of the building would have broken first at the depth where the interface between the soft and stiff clay layers was located. So actually dia giving you the idea from the simulations, rupanya dia dah ada some signal untuk berlakunya structural failure. And then they plot again the pure bending capacity pile along the excavation dan juga pile near the dump site. So satu represent north and also south side. So it says that the bending capacity of the piles on the excavation side of the building was exceeded, and this pile failed before those on the soil dumping site did. The embedded pile model, which actually consists of elastic beam elements, were adapted, and the breakage of the pile could not be simulated in the analysis. So this is the reason why the bending moment kept increasing after the bending capacity was exceeded. So ini antara kelemahan lah yang boleh kita dapati daripada simulations lah, because they can give you the result until what's end. Ini memang perlukan some expert ataupun engineer yang very familiar doing the simulations, and then they know when to cut off the readings. So ini yang stated by the researchers. So what can we conclude from the post failure is that at the north side of collapsed building, uppermost fractures could be seen near the interface between the reinforced and unreinforced section, which were located approximately 1 to 2 meters below the original level of the pile head. Most of these failure surfaces were flat, implying that these piles failed under the tensions. Meanwhile, at the south side of the collapsed building, the pile situated under excavation side of the collapsed building, the uppermost fracture surfaces were tilted at the angle and the concrete was severely damaged. So these fractures occurred mainly from compressions, and the largest bending moment was developed in the piles on the excavation side of the building at a depth corresponding to the interface of the soft and firm stiff clay layers under the combined effect of excavations and dumping. So these results were based on the conclusions were based on the results found from the simulations analysis. And the schematic images show to you what's exactly happened at the site for the building number 7, 13-story building. Okay, what are the lessons learned? The geotechnical engineers and contractors should be better trained to improve their understanding of the effect of surcharge loading on PHC piles, and the proper construction procedures and site supervision schemes should be explicitly spelled out. Engineers who design foundations in soil regions to consider not only the final loading conditions, but also any temporary and transient loading conditions during the construction process. And again, as I said, kalau you doing for the analytical calculations, selalunya kita terus ambil sekali the effect of field height 6 meter ke ataupun 10 meter, 4 meter, kemudian kita buat calculations, kita tengok dia punya settlement. Tapi kita tak nampak sebenarnya bila dia menunjukkan benda yang berbeza kalau melalui simulations. So simulations ni you can give extra input or additional factors yang mana kita tak boleh dapat secara on analytical calculation saja. So we can add on, for example, the other effects or the other factors to the soil structure problems or interactions. In the summary, it is evident that for this case history, the effect of the temporary embankment filling adjacent to the building may not have been properly taken into account in the foundation design or in the constructions. So simple but important lesson is that in order to successfully design a foundation in the soft soil area, engineers not only need to consider the final loading conditions, but also any temporary loading such as those might arise from the storage of construction materials and construction generated waste soil. Okay, that's end for the case history in Shanghai. The simple thing is that for geotechnical area, if you want to start off doing your constructions or whatever, first thing is to know the geological formations. For example, kalau you pergi dekat bahagian belah Perlis, you pergi bahagian Penang, so the geological formation tak akan sama. So maknanya project site untuk setiap tempat berbeza. So that is coming importantly to have the site investigations. When you have the site investigation report, then you know what is the best design and construction activity methods untuk you adopt in your project. So most of the problems in soft soil selalunya dia kena ada soil improvement dah, sama cara dia soil stabilization ke, you nak pakai soil reinforcement ke, whatever it is, you need to treat the soil first, barulah you start buat construction piling ke apa benda, atau any advanced construction activity menggunakan ground improvement, contohnya vibro compactions ataupun you nak menggunakan ground stone column kat sini. So any question before we proceed with the next chapter 4? So let us have a 5 minutes break. Okay, let us start on having a new case for chapter 4. So chapter 4 berkaitan dengan excavation. Okay, so let us start having this watch video dulu. Okay, so daripada video ni, okay, kes tadi kita malam ni kat mana? Seterusnya. Siapa boleh jawab? Okay, kita minta Encik Nur Hisham lah. Kes tadi kita seterusnya di mana Encik Nur Hisham? Okay, any answer? So what was our next case study and the location?
Dekat negara jiran kita, Singapore, Nicole Highway.
Tahun 2004 tu kan?
2004.
Rasa-rasa daripada video tu apa dia punya impact dia? Ataupun daripada case collapse tu apa yang menyebabkan dia jadi disaster, kemudian dia jadi historic news and then dia jadi become hot news that year.
Like macam saya pernah lah baca sikit pasal Nicole Highway ni. Yang saya tahu, yang saya ingat-ingat lah. Ada tunnels ni dia linking dekat satu macam station tu, dia macam cave lah. So dia dalam juga. So yang runtuh tu adalah retaining wall disebabkan soil subsidence. If I'm not mistaken.
Ada jawapan lain? Thank you for answer the question. So if you look at to the previous case study in Shanghai, the collapsed buildings will not affect to the human lost life. So this Singapore collapse, I mean that the Nicole Highway collapse affected to the loss around 4 people. So dia menjadikan satu hot news lah sebab whatever constructions you are trying to do, things first yang kita kena consider adalah safety, kemudian the social impact, environmental impact dan juga economical impact. So if this thing already happened and occurred in the Singapore, pada ketika benda dah berlaku, bila dia kehilangan 4 nyawa, so dia dah jadi hot news in the region. Kemudian the social impacts adalah banyak benda yang akan terhenti daripada urusan biasalah. Contohnya akan ada traffic congestions, kemudian dia dah menjadi satu kawasan tumpuan dan economical pun mungkin terjejas, mungkin harga saham pun akan terkesan because kalau you tengok Singapore is very well developed country dan dari segi dia punya fine, dia punya rules, dia punya whatever it is very strict dan kita as a tourist dekat kawasan tu pun kita amat berhati-hati berbanding kita berada di negara kita sendiri. So these are the things yang menjadikan Nicole Highway ni antara common case study to re-evaluate on part of the forensic investigations ataupun on part of the forensic assessments. So yang lagi menariknya berkaitan dengan Nicole Highway ni yang mana dia adalah satu megastructure yang bukan hanya untuk bina jalan tetapi dia lebih kepada to provide infrastructure iaitu MRT, and never expected that due to the satu structure menyebabkan runtuhnya jalan raya tersebut. So from the video itself, I think that you can see that actually dia ada four bodies yang sepatutnya dijumpai tetapi only 3 were found and the other ones are still missing and memang dah hilang lah. So itu antara kesan-kesan ataupun the historical news on part of the Nicole Highway. But today we're going to see from the geotechnical aspects macam mana Nicole Highway ni boleh berlaku dan sedikit historic background on Singapore sendiri. So kalau kita tengok Singapore ni dia adalah satu dia kalau ikutkan Johor kemudian dia boleh consider as an island lah. So kalau kawasan tu dia memang terhad dari segi original land ataupun original soil dia. So this part of this construction site ni dia adalah satu kawasan reclaimed area daripada alluvial ataupun marine soft clay. kemudian reclaim for the purpose of infrastructure developments. So you can see they are different resulted to the soil profile. Originally soil profile tu adalah marine clay, tetapi untuk tujuan constructions ataupun MRT purpose, dia dah buat tambak tanah, dan dekat situ pun dia dah bagi contrast on the soil profile. So bila talking about marine clay ni, selalunya orang memang tahulah low shear strength, kemudian dia kena buat soil improvement. So benda-benda ni yang mungkin sepanjang construction activities ni ada yang terlepas pandang ataupun ada yang sedikit silap pada peringkat design dan juga analisis. So itu yang kita akan cuba tengok dan kupas untuk malam ni. Okay, for the learning outcomes, so if you notice here, so this is will be on the chapter 4, Race Excavation Collapse, Nickel Highway Singapore, and our learning outcomes are to discuss the brace wall stability, to evaluate the failure cases using relevant theory, to propose mitigation measures related to foundations failures. So these are the very common framework kalau you ada case study ataupun post-failure analysis. So the first case, we begin with the case descriptions sebelum kita boleh bedah siasat lebih dalam dari segi dia punya analisis dia, kemudian mitigations dia, dan juga apa yang kita boleh ambil pengajaran daripada case study. So the island city-state of Singapore has one of the best public transport in the world. So yang ni memang dah diakui lah. So the mass rapid railway network is the main backbone of this system. So the constructions of new 33.6 km long underground circle MRT line CCS started in 2001. So costing approximately 6.7 billion. So the CCL will link all the radial lines leading to the city. So after 3 years lah, maknanya lepas projek tu dah initiated, so dia failed lepas 3 tahun lah. The first stage of this construction, CCL1 was 5.4 km long and was subdivided into 2 contracts, C824 and C825. So saya rasa ada yang di antara kita memang quite familiar with the projects. So tender, macam mana dia nak assign, and berapa total cost project. So I think that this quite similar lah kalau ikutkan dia punya long lah, dia punya track tu panjang 33.6, and then dia split into few contracts, and you can see the CCL lines from the CCL1 to the CCL2. So kira kata this is the massive MRT construction lah for that particular area, for that particular year. So the design, so part of the contract ataupun tender dia menggunakan kaedah design and build. C824 comprises of Nickel Highway and Boulevard stations, 800 meter of bored tunnels, and 1,600 meter of cut and cover tunnels. So the main contractor for this works was the Nishimatsu joint venture. So the client was the Land Transport Authority of Singapore. So the chronology of the problem, around 3:30 p.m. April 20, 2004, the 33.5 meter deep cut and cover excavation required for the constructions of tunnel between Nickel Highway and Boulevard stations. So kalau ikutkan dia boleh nampak from the red circle lah. And the collapse was catastrophic, resulting in 4 fatalities and a lot of damage. So which delayed completions of the CCL1 stage by 4 years. So CCL1 tadi yang ni lah, CCL1 dia punya jajaran daripada from the right to the left side here. Boulevard started until to the end of the convention center ataupun Derby Gate. So bila I say lah, bila this failure occurred, dia memberi impact to the social, dan kesannya is back to nak back ke normal, dia ada benda-benda lah terkesan kan. So the Singapore government appointed a committee of inquiry COI to ascertain the causes and circumstances of the accident. From the report in 2005 submitted to the government and the public on the internet, the main source of the information for this chapter were found. It concluded that the computer-dominated age sound like a paradox, which a wrong use of numerical modeling in geotechnical design, together with some structural errors, were the main causes of the Nickel Highway collapse. So in the summary, released in 2005, stated these are 2 main causes to the Nickel Highway collapse. But as I said again, some numerical modeling and simulations is very good and helpful in your analysis kalau kata the engineer and the persons are very familiar with the software, then having a good knowledge about the problems ataupun the fundamental of the geotechnical engineering or whatever, sama ada geotechnical ke structure ke apa benda. So with the experience blend with the knowledge, insyaAllah dia akan produce a good results lah. But again, they need to the second checker untuk lihat semula lah the output of the simulation. That's why when you are doing the simulations or numerical analysis, the next thing yang you kena buat adalah verification result ataupun validation result. So the main of the reason why we do the verification and validation to check our results is through by comparing to the analytical solutions or any kind of the software. So itu cara untuk pastikan numerical yang terhasil ataupun result yang terhasil daripada numerical solutions tu adalah benda yang betul. So now the summary 2 reasons sahajalah, tetapi kita try to look at in details. So bila cerita pasal excavations activity, meaning that the thing is not easy, dan selalunya excavation depth tu not 3 meter. They can go beyond 3 meter. For example, here 33.5 meter depth. So in this thing, bila kita nak retain soil from movement, yang kita perlukan adalah wall. So dalam this case, it can be any kind of the retaining wall. For here is a diaphragm wall. Dalam thickness dia 0.8 dengan dia punya kelebaran antara satu wall kepada wall yang lain dalam 17 hingga 20 meter jarak dia lah. Okay. Dia menggunakan design and construction method iaitu cut and cover tunnels for the contract C824 using the bottom up method. So the diaphragm wall used at this section at the cut and cover tunnels was 0.4 meter thick and penetrated 1 to 3 into stiffer strata at the depth of about 40 to 45 meter. So ikutkan kalau daripada statement ni kita nampak lah sebenarnya diaphragm wall tu dia dah mid to the hard stratum around 40 to 45 meter lah. Kalau ikut excavation depth yang diperlukan around 33.5 saja. So basically we can assume that impossible nak berlaku any kind of the failure lah, sebab kita dah nampak it is well stand at the hard stratum. And the 2 layers of jet grout slabs constructed using interlocking jet grout piles were also installed after construction of the slurry walls to minimize deflections and ground movement during the excavation work. So ini pun salah satu kaedah lah untuk soil improvement teknik, iaitu menggunakan jet grouting piles. So the upper 1.5 meter thick layer of JGP was placed about 28 meter below ground level. The lower permanent 2.6 meter thick JGP layer was built 33.5 below the ground level, and the excavation was kept open by a strut system comprising of steel king posts, wallers, and 10 level of struts. So the strut was spaced at 3.0 to 3.5 vertically and 4 meter horizontally. So the width of excavations was about 20 meter and it was about 33.5 deep. So all these informations are given as you see from here. So at the right side of the slide, you can see the details layout plan, affected area, dan juga the kind of the monitoring systems. So during the constructions, there were some installations of the instruments such as settlement marker and also vibrations wire piezometer, and lastly is the inclinometer. So the monitoring or instrumentation tool are helping to provide in situ data, for example, the water level height, the height of the water level, and then the soil movement. So actually it can be predicted by looking at this data collect at the real time. So kalau ikutkan details lah kat sini, instrumentation layout dah banyak, settlement marker semua dah provide, piezometer pun dah ada, so nak baca ukur tinggi aras air, inclinometer pun sama. So as I said, dia boleh berlaku jugalah, unexpected. So an extensive monitoring system was installed, included more than 2,000 monitoring instruments, settlement markers, inclinometers to measure soil and water displacement, vibrating wire piezometers to measure pore water pressure, strain gauge, and load cells to measure the strut loads. So the readings from the inclinometer 1665 and 1104 and strain gauge and load cells in the strut S335 are crucial for understanding the cause of the excavations collapse. So if you look at here, the next thing when they did on the back analysis or post failures, so these instruments are given the importance data to analyze for the causes or reasons behind the failure. So the COI report states warning of the approaching collapse were present from an early stage, but these were not taken seriously. Indeed, as early and in August, it became clear that something was wrong with the design, meaning that they already detected in August 2003. First, in the launch shaft for the tunnel boring machines across the river east from the collapse area, measured wall deflection exceeded 500 millimeter, while the calculated design level was only 190 millimeter. So this is the early sign actually something can happen. So never know who were wrong at that time. This caused damage to the returning walls, ground settlements, and crack at the cricket field nearby. And the figure 6.5 showing to you the displacement of the southern wall in time. You can see from the beginning, they captured the data in the early October 2003 until to the last 70 April 2004. So the maximum deflections or displacement occur in the January 2004 and 20 January 2004, with the maximum displacement around 253 millimeter. So at here, they can say actually this is something can be given important data or important early warning, but who knows at the time the data will not capture or any other reasons. So in the January 2004, the design deflection level was exceeded and cracks appeared in the retaining structures in the cut and cover excavation west of the collapse area. So the design deflection level had to be revised upwards from 222 to 522, from 125 to 313 millimeter closer to the collapse area. This was accompanied by numerous complaints received from the owners of neighboring properties, including ground settlements of driveway cracks in the building and other building damage. So manpower resources from the CA24 project team were deployed to handle the repair works. So they thought that at the early sign detect on the highway crack and the structure crack, it's thought that very simple problem and nevertheless to check on the ground movement and also the settlements, and what they did on repairings only. And the extensive monitoring, as mentioned just now, around 2,000 instruments were marked nearest to the construction site. So the deflections accompanied by buckling or valley stiffness plates, which were replaced by C channels starting from the 7th level. On the basis of bad analysis, it was decided to update the design level to 253 millimeter and increase to the preloading of the strap from 50 to 70%. So this is another thing that they found. They should be adjusted, or they need to redesign, reanalyze to what supposedly, because they already got the data from in situ monitoring. So supposedly they need to change previously design and analysis to the current design and analysis based on the instrumentations data monitoring. Unfortunately, did not have. In the end of March 2004, the new design level was exceeded again. Another bad analysis produced another revisions of design level up to 359 millimeter. Nevertheless, when the last measurement was taken on the day of collapse, was exceeded by as much as 22%. So actually, from this statement, the case study is quite difficult to write up to produce a good writing, because something if you have a complete set of the data, they can produce a good case study report. If you cannot gather all the data, for example, you do not provide any field instrumentation monitoring, and then you do not keep any design and analysis prior to the constructions, in between of the constructions activity and the last design and analysis. If you not keep all this data from the beginning to the end or to the last day of the collapse, you cannot produce a good report. For example, this Nicole Highway is very good at detailed explanations on the case problem. Therefore, it is very common case study being revised and reanalyzed by other researchers to look back or to reanalyze or reevaluate in different perspective. So on the day of the collapse, the 9th level of struts was completed and the excavation proceeded to the final 10th level. In order to achieve that, the first temporary layer of JGP had to be excavated. So in the morning, the workers were carrying out excavation work and preparing to install the 10th level of struts. And this is happened. So they heard a town sound and the excavation base frequently, there were water beams buckling. So maknanya mereka tak boleh nak buat yang seterusnya lah pada nombor 10 sebab failure dah berlaku. To strengthen the water beams, it was decided to pour concrete into their top sections. Maknanya failure berlaku pada this part. So they tried to repair dengan masukkan concrete lah. But did not have the beam were already too distorted to hold the concrete. And the frequency of the town sounds increased. Maknanya it's become worsen lah. The first sound tu dah indicates that the structures nak slowly getting severe lah, damage. The frequency of the town sounds as it increased, another contingency measure pouring lean concrete into the excavation base to replace the excavated GP slab came to lead. At about 3:30 p.m., a section of the temporary diaphragm wall supporting the excavation adjoining to the Nicole Highway Station box had collapsed. So when you're reading out this one, you can find the problems occur when they try to add another slot level number 10, but unsuccessfully because it's already started to collapse. So this caused soil subsidence of the immediate surrounding area, which propagated rapidly, covering approximately 100 and 130 meter area and sucking in the heavy equipment. It did also result in substantial damage to about 100 meter sections of the Nicole Highway carriage adjacent to the abutment of Merdeka Bridge, and the incident has resulted in 4 fatalities, where 3 construction workers and 1 engineer and 3 injuries. Fortunately, no motorists were travelling along the sections of the Nicole Highway when the incident happened. Otherwise, the number of deaths and injuries could have been even higher. So, bagus jugalah walaupun terkesan sikit dengan kematian, tapi dia tak menyebabkan banyak nyawa. So ini antara gambar yang menunjukkan strut buckle started to have the problems. So ini yang explain just now. Kalau from the report, dia hanya bagi two important causes failure daripada wrongly estimate in the numerical modeling simulations, and also the other one is the negligence to follow the standards. So when we look back to the problem, we try to investigate from the geological formations or from the geotechnical data. So the site investigation indicate that the soil profile can be divided into the following strata. As I said earlier, the field or the area was reclaimed 20-50 years ago, and the water level is 2 meters below the ground surface. The estuarine organic deposits, upper and lower marine clays, and more of fluvial and estuarine deposits. So these soft clays are underlain by stiffer sands, silt, and clays of the old alluvium. So the best estimate of the undulation strength for Prism test is given in the figure 6.8. So here, this is the undulation strength test. This is important if you want to do the back analysis or you want to calculate the strength of the soil as well as the soil structure interactions problems. And you can see from here, the upper and lower marine clays and more fluvial and estuarine deposits. So sini pun dia dah bagi tahu tanah ni very weak part of the strength parameters lah. Kemudian alluvium ni is one of the transported soil ataupun soil yang terbentuk daripada transported rock. So bila dia dah transport ataupun dia dah bawa kepada satu kawasan, selalunya pantai lah akan dijumpai tanah-tanah jenis ni. So you can see that the strengths not very high berbanding dengan tanah kalau you jumpa dekat kawasan batuan granite ke ataupun residual soil yang jenis granite. Okay, the combined together these errors resulted in considerable under design leading to the failure of the retaining structure. So replacement of the stiffener plates, by C channels change the mode of the failure from ductile to brittle. Other significant contributing causes were wrong use of the geotechnical bed analysis and inefficiency of instrumentations and monitoring systems. So on this statement, I'm not sure why it says that, because if we looking at the previous data, there were around 2,000 instruments placed near the construction site. So for me, 2,000, quite huge number, and maybe for that large area, 2,000 is not enough. So they need more. Additional contributing causes could have been insufficient to penetrations of the diaphragm wall into the impermeable strata or lower than expected JGP strength. So these are other causes that may give to the Nicoll Highway collapse. A long times at which excavation was left unsupported, so no strut failure check in the back analysis. In this chapter, we focus on the main geotechnical aspect of the Nicoll Highway collapse, a wrong estimate of undrained shear strength, and as a result of the lateral earth pressure. So if you can, what we call it, you try to recap what we had learned previously in the chapter 3 from the previous two cases study. The first and two is it is on bearing capacity failure. So today for this case, or for chapter 4 case study, the failure is on part of the excavations failure. So the application is on returning wall. So you can have the difference failure mode, which is not similar to what we had learned previously from two cases. So the two cases on the bearing capacity failure, and today is the excavations failure. So you can see the effect of the wrongly designed or estimated has resulted to the retaining wall fail. So the mode of the retaining failure, it can be overturning, it can be some sort of this kind crack, or it can be sliding. So these are the common failure mechanism for retaining wall. For this kind of excavations, again, if you look at, there should be a problem related to the structure. However, for this case study, it's only try to focus the wrongly estimated on the shear strength analysis by numerical software. So that's their aim. So this is the image for figure 6.8, the soil profile classification for that site. From the beginning, you can see two different sections of the original soil and also the fill material. The original soil is estuarine, which is fluvial clay at the bottom, and part of it is reclaimed soil, which is around lower marine clay, fluvial clay, upper marine clay, and estuarine soil. And the undrained shear strength for here, you can see the dash line is results from the finite element analysis, and you want to estimate the best value for the undrained shear strength. It is maybe at this depth. Pada 20 meter ni, ini yang best value lah untuk kita dapatkan the undrained shear strength. So again, just to recap, these are the important informations, 30 meter deep excavation, then history about the failure, the reasons collapse occurred. So kalau ikutkan as I explained just now, ada dua lah, iaitu deficient monitoring dan juga error during the design. Macam mana dia berlaku, ini pun dah inform, which is the retaining wall could not handle the stress of holding up the tunnel and forcing it to give way. So this occurred near the Nicoll Highway MRT stations under constructions. So not to forget, when we're talking about the excavations or retaining wall applications in geotechnical study, it is about on the lateral earth pressure or lateral earth stress. So once we have the overburden pressure, not to forget also when there is another stress effect to the structure, which is lateral earth pressure. So the lateral earth pressure coming horizontally, when the soil is subjected to the excavations, you release the stress, and you can see some soil will move towards the wall or far away from the wall. So if the wall in the stated condition, we can see that is the rest condition. So the wall in safe part. However, if you having some additional loads, for example, surcharge on the ground surface, and then the other effect of the water table, so this can resulted to the lateral earth pressure inactive, which is the wall move away from the soil. If the kind vice versa, if you have the wall move toward the soil, that is the conditioned soil in the passive states. So you can see there's another equation that will be related to explain about the overburden pressure and also the lateral earth pressure. So this is why I try to explain the stress that we found from here is related to the lateral earth pressure or lateral stress. The key lessons from here, the trends of the temporary work during critical periods must be capable of being monitored, and those interpreting the analysis output must be competent to do so. So the problem. So these are the informations about the soil profile at the area. And the same reasons, a wrong estimate undrained earth pressure acting on the retaining structure, the structure, and error in design of the bearing capacity of the wellers. So reason number 2 ni kita tak tengok lah, kita try to look at the main problem from the geotechnical aspect. Okay, this is the same image. Okay, ini pun few factors, antaranya back analysis in efficiency of instrumentations, and then insufficient tube penetration, diaphragm. Maknanya sebenarnya diaphragm wall tu dia tak masuk pun dekat kawasan hard stratum. Itu antara yang they assume. And then the lower the no strut failure check in the back analysis, maksudnya dalam design ni dia tak include also strut characteristic ataupun strut properties. Okay, the major causes of the collapse including the following: errors in the design of the strut to wall connections through erroneous back analysis, deficient monitoring at the site, incorrect use of the computer programs. The contributory causes were listed as follow: inconsistency between design criteria and codes, insufficient to environment for hydraulic cutoffs, special geometry not taken into account, cable crossing disrupted diaphragm walls and JGP slab, inadequate appreciations of complex grounds conditions. Of course, it is very complex because kalau you tengok, walaupun kita nampak on part of the soil from the top to the bottom, nampak macam jenis soil formation yang sama, tapi the process of the reclamation occur few years after. So the current stress and the previous stress dia tak sama. So stress macam clay ni dia boleh ada normal consolidated clay, dia boleh ada over consolidated clay, kemudian dia akan ada pre-consolidation pressure. So these are other factors when you want to analyze the soil type such as clay. So kalau you analyze foundations ataupun excavations in sand, they will be also resulted in different value, part of the lateral stress pressure ataupun lateral earth pressure. So when you want to analyze, firstly you need to know what's our application geotechnical you want to do, and then it will be laid on what soil type, and then you identify the strength parameters and also what are the soil models. Kalau benda-benda ni dah complete, so you can proceed with the analysis. So this is the theoretical part. Basically, when we want to analyze, we need to ensure, is it our structure is a short-term stability or long-term stability? Just to show you the differences between long-term stability and short-term stability. For example, talking about the strength parameters and then the strength value. If you have the long-term stability, it's a drain shear strength. This is why you call it as a drain shear strength. Is a period of time that you allow the water dissipate from the soil structure. So the long-term stability then can have a drain shear strength. Or you can analyze for the long-term stability using the drain shear strength parameters by having the effective stress analysis, which there is no excess for water pressure dissipates for the calculations and resulted to the effective C and also effective P. For the short-term stability is the undrained shear strength. It's very occur in shortly. So the analysis using the total stress analysis and the excess for water pressure dissipate, and the parameter or the symbol for the shear strength is a CU or undrained coefficients. So we want to analyze from the retaining wall theoretical background. So imagine that at the left side of this image, we have a pressure diagram. So the triangle shape is showing to you the pressure diagram. From the top is the ground surface, and from the bottom or to the depth Z, assume as a Z. Ideally, when we calculate the overburden pressure or the effective stress, vertical stress at the ground surface, this is ground surface, for example, Z sama dengan kosong. So contoh unit weight of soil sama dengan 10 kilonewton per cube meter. Actually, I try to explain how the triangle pressure diagram produced. So by simple theoretical understanding, if you having this diagram A, effective earth pressure, which is free standing wall, and satu lagi case yang mana brace excavation. So kalau you tak ada problem excavation, so kita boleh ambil diagram number 6.10A ni lah. Kalau you buat analisis retaining wall yang melibatkan excavation, so the pressure diagram you kena refer pada B. Okay, kita tengok pressure diagram dekat bahagian kiri lah. Kalau kata dia melibatkan analisis untuk simple retaining wall saja, tak melibatkan excavations. You want to install or you want to construct a retaining wall vertically wall. So the pressure diagram effective ni yang mana maksudnya the effective stress is calculated having the total stress minus with the effect of pore water pressure. So pore water pressure, kalau you ada effect of the water table, contohnya kita ambil unit weight of water 9.81. In this particular case, for example, kalau there is no water table effect, so we can see that the effective stress is equal to the total stress. So total stress kat sini, effective stress kat sini, by simple calculation, we can assume that unit weight of the soil times with the depth. So kalau kata you want to calculate the vertical effective stress at the ground surface Z sama dengan kosong. So 10 darab dengan kosong, so kosong lah. So betul lah ni dia punya diagram. Mula dekat sini kosong. But once you go into 1 meter deep, pada kedalaman 1 meter pula, so you can replace lah. Sekarang ni kita nak calculate effective vertical stress. Contohlah effective vertical stress sama dengan 10 kali dengan 1. So you akan dapat 10 kPa. So ini adalah vertical stress. Sebenarnya yang kita nak dapatkan adalah lateral stress. So vertical stress dia vertically, dia dalam arah vertical. So kalau lateral stress, laterally lah. This is the lateral stress dan resulted to the lateral force ataupun lateral thrust. So the lateral thrust ataupun lateral stress dulu, sigma H effective ataupun total is equal to the coefficients of earth pressure times with the effective vertical stress. This is what I said. Kalau you punya retaining wall ataupun soil you dalam keadaan rest conditions, so that K is a K naught, coefficients of lateral earth pressure. So macam kalau kata dia dalam keadaan aktif, so the coefficient active earth pressure boleh calculate menggunakan equation 6.2. 1 minus sin phi bagi dengan 1 plus sin phi. So once you have the Ka, you multiply with the effective vertical stress, you akan dapat lateral earth pressure lah. So Ka darab dengan sigma V. So theoretically, we can say that if the vertical stress increased by depth, same or similarly to the lateral effective stress. So the lateral effective stress will be also increased by depth. That's why it gives you the triangle shape ataupun the pressure diagram dalam bentuk segitiga. Sebab mula-mula kita mula kat kosong, Z sama kosong, so kosong lah kan. Makin naik, makin dalam 1 meter, 2 meter, 3 meter sampailah 10 meter for example, you akan nampak the pressure increase. Tapi kalau kata you nak buat excavations and then you letak wall dekat kiri dengan kanan, so the pressure dia dah tak sama lah triangle tu, dia akan jadi square shapes lah. And this case dia pasang lagi strut H, so dia ada force lah, horizontal force 1, 2, 3, 4. So bergantunglah kepada jarak strat antara satu strat dengan strat yang lain. Okay, in the bridge excavation, displacement are not large enough for an active failure state to develop. So in this case, according to Terzaghi, the effective force will be 30% larger than in the freestanding wall. The earth pressure diagram becomes rectangular. This is what it explained lah. Okay, for the undrained shear strength, to estimate the undrained shear strength, you can have experimental testing by conducting unconsolidated undrained, ataupun you boleh conduct vein test ataupun cone penetration test in the normally consolidated clay due to development of the positive excess pore water pressure during undrained shearing, the effective stresses decrease as seen in the figure 6.9b. So this experimentally determined undrained CU to be significantly smaller than clay strength at the same initial effective stress in the drain shearing. So an empirical rule of thumb giving the following approximate relationship for the undrained shear strength of normally consolidated clay as here. So the undrained for cohesions, undrained shear strength, normal consolidated clay, you boleh calculate pakai this formula 6.5. K sama dengan 0.21 sehingga 0.25 lah, bergantung kepada value ataupun clay type. So the effective V0 is the in situ geostatic vertical effective stress. So the lowest values of K 0.21 are valid for soft marine clay, which is the case Singapore, and the shear strength values for original design in figure 6.b apparently based on the CU equal to 0.29 times dengan effective V0. Using the effective stress approach, the different constituent model predict the relationship 6.5 with a different degree of accuracy. So it says that kalau you pilih K sama dengan 0.21 ke, you pilih 0.22, 0.23, 0.25, so dia boleh bagi nilai undrained yang berbeza. So bila you pilih, contohnya seorang ni pilih 0.21, seorang ni pilih 0.22, seorang ni lagi pilih 2.3, seorang lagi pilih 0.24, 0.25. So you akan nampak the variations value of the undrained cohesion, and somehow it also can be shown through the diagrams. So this diagram is actually showing to you the critical state of the soil or critical path. So kalau you ada initial pressure of the soil at this point, this is mean stress, P, and Q is a deviated stress. So initially dia pada this value, and then it can be decreased until it meets to the failure line. So the tangent line here indicates to you the failure critical line. The failure critical line is the line where the soil deform or fail. So kalau you menggunakan two ataupun you menggunakan more column model, very rare untuk you dapat this case. Selalunya more column model untuk undrained, dia akan naik ke atas. That's why it is said what we call it as a overestimate. Yang sepatutnya failure tu berlaku dekat sini, tapi more column dia assume atas lagi. So maknanya dia tak represent real soil ataupun real behavior of soil. So that's why in this particular problem yang melibatkan soil structure, you have to choose correct soil model. Bila you pilih correct soil model, that can predict the correct soil behavior at sites. So that's why I said kalau kita pilih model yang betul, contohnya failure berlaku pada stress sama dengan 50 kPa. Tapi bila you model menggunakan more column predict ni atas lagi. Maknanya bila kita model pakai more column, failure tu berlaku pada 100 kPa. So kita assume selamat lah. Padahal bila realitinya untuk clay problem ni, dia boleh jadi drop. That's coming to the error design. So the normal to slightly over-consolidated clay have a tendency to contract during drain loading. So this water is incompressible in undrained shearing. So this results in positive excess water pressure. The corresponding effective stress path to failure in PQ drives the stress space curve to the left from vertical and hits the failure envelope as much lower deviated failure stress related to undrained shear strength via QF is equal to 2CU. QF is a compressive strength. So kalau you nak dapatkan undrained cohesions, so QF kena bahagi dengan 2. So this is what I said more column model for the critical state Untuk Molecular model, it is assumed isotropic elastic behavior during pre-failure deformations. So in under-interiorization loading, when there is no volume change allowed, so the result is no pore water pressure being generated. So the mean effective stress P stays constant and equal to initial mean effective stress P naught. And the corresponding effective stress path to failure PQ striated space is vertical. This is what I explained just now. So it's assumed that QF sama dengan MPF, M equal to P naught. M is the critical slope line gradient. M can be calculated is from equation 6.7, and the mean stress or P naught, it can be calculated from the equation 6.8. So the K naught is the at-rest earth pressure coefficient, which for normally clay is calculated from 6.9 equations. And substitute equation 6.7, 9 into 6.6, and noting that the undrained coefficient is equal to the QF over 2. So, since Cu sama dengan K times sigma effective V naught, so finally we can have the K here is equal to sin effective phi 3 minus 2 sin phi over 3 minus sin phi. So this is a typical range untuk dapatkan phi effective, K effective dan juga the other relationship for equation 6.5. I think that is enough. Modified chemically is a very a bit difficult compared to more column. So I think that better I stop saying the more column. You get familiar first with the more column before we go to the extensive advanced model for soil, which is modified chemically model. You have to understand the more column dulu baru boleh faham kepada modified chemically model. Is there any questions before we end our class tonight?
Doktor, I just want to know the Z value punya depth tu kan, dia akan berbeza ke kalau ada different type of layer of soil? Maksudnya kalau ke atau dia pakai rule of thumb juga?
Oh, so firstly, kalau you ada SI report and then you conduct for SPT test, so better you use that data. Memang for sure kita takkan dapat the same soil profile from top to the hard stratum. So there's another empirical correlations or relationship to give what is the strength based on the SPTN number. Ataupun kalau kata you want to analyze for bearing capacity, so find the right equations untuk you dapatkan the bearing capacity based on the site data. Let's say you tak ada SI data, site data kan. Kemudian you want to do the analysis. So you need to get the typical data commonly used by other researchers. For example, kalau you want to study in Malaysia or in certain particular regions area, you need to know lah. Kalau dekat, macam saya beritahu lah, you nak buat projek dekat Perlis, you tak boleh ambil data daripada Penang sebab totally geological formation berbeza. So then you have to get the nearest data site yang boleh provide the same data. Kemudian kalau kata tak ada juga, you can have the typical data from any articles, for example in Malaysia, but the range value tu you have to be careful and look at what soil type. So kalau you dah boleh identify soil type dia, you akan nampak lah sebenarnya kalau you ada different soil strata, that can produce you different soil strength or undrained coefficients ataupun Ventia data. Tapi kalau kata you want to analyse at particular depth saja, so kita tak perlulah ambil the variations of the undrained coefficient. You just can get the average coefficient pun, that is enough.
Alright, okay. Thank you, Doktor.
Okay, we end our lecture tonight. I'll see you next week. Have a nice weekend, everyone, and goodbye and Assalamualaikum.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.
Doktor. Thank you, Doctor.